In this presentation, we overview Galileo's contributions to kinematics. But to begin, we consider Galileo's timeline. So he was born on February 15th, 1564 in Pisa, and about 3 decades later he was appointed the position of mathematician at Padua in 1592. Now, during this time at Padua, he was able to make significant contributions in his own personal study to kinematics. But in 1610, he published the Starry Messenger, which then changed his focus to astronomy. Specifically, Galileo around this time began observing the solar system through the telescope, and for example, he saw that Jupiter has moons, and moreover, our moon has mountains. So with these kind of observations, he put that into the Starry Messenger, which began Galileo's dislocation of the Earth as being a unique celestial object within the solar system. Next, Galileo in 1613 would publish letters on sunspots, which, for example, describe that the sun rotates, which causes the sunspots, and moreover, that Venus has phases just like our moon. And then in 1616, he published On the Revolution of Heavenly Orbs, which supported Copernicus's theory of a heliocentric solar system. But because this contradicted the Church's geocentric theory, the Church would then warn Galileo to stop pursuing and openly teaching such heretical theories. And for a while, Galileo would in fact would observe this warning. So, for example, in the Assayer in 1623, he described such non-controversial topics as how comets were sublunary objects. Moreover, what was really interesting about the Assayer was that Galileo actually claims that the universe, all of nature, could be described in the language of mathematics. But then in 1632, Galileo published his most controversial work, that being Dialogues Concerning the Two Great World Systems. And this one, again, Galileo supported Copernicus's theory, and because of this, the Church, through its Inquisition, persecuted Galileo, labeled him a heretic, put him under house arrest for the rest of his life, and would prevent him from publishing any other further research. But while in house arrest, Galileo refined his uncontroversial work on kinematics, and in 1638 he smuggled discourses and mathematical demonstrations concerning two new sciences. He smuggled that out of his home to Holland, where the Church had less influence, where he was able to get that published. This work gives Galileo's definitive treatment on kinematics, namely since in 4 years later he died in 1642, where he was subsequently obscurely buried. He was obscurely buried because of his heretical label that the Church's Inquisition put upon him. So we now begin discussing Galileo's actual thoughts on kinematics. And to begin, we consider his unpublished manuscript, De Motu, which criticized Aristotle's theory of matter. For example, Aristotle believed that matter could be classified as one of earth, air, water, fire, and then could be further subclassified into heavy and light. Galileo, on the other hand, thought that all of matter should just be classified as variations of heavy. But more to the points of kinematics, Aristotle argued that heavy objects should fall faster than light objects. But Galileo, in turn, argued that such a hypothesis from Galileo would give a reductio ad absurdum. And we now describe Galileo's argument below. So, suppose that we are given two differently weighed objects, and we're going to suppose that the filled-in circle here is heavier than the non-filled-in circle. Then by Aristotle's theory, the heavy object should fall faster, and so we get this relation. But what would happen if we glue the two together? Well, possibly one interpretation is that since the lighter object falls slower, then the heavy object is going to have to slow down in order to pull the lighter object along. But alternatively, the two glued together objects certainly have a greater weight than either of their constituents. Thus, the glued together object should fall faster than the heavier object, but then this contradicts the well-definedness of our relationship between how quickly objects should fall in relation to their weights. And thus, certainly, falling objects, their speeds cannot be described just by their weights. Galileo would then further argue that all objects should fall at the same speeds in vacuum. But those previous arguments didn't really get at the nature of predicting how objects should move in nature. In order to do so, Galileo then formulated this definition. A motion is said to be equally or uniformly accelerated when starting at rest, its momentum receives equal increments in equal times. In other words, uniform acceleration describes a velocity that increases linearly with time. This will then allow him to actually make predictions of how position changes with respect to time under uniform acceleration. But in order to actually describe such a position, working directly with acceleration is not very useful. So Galileo also introduces the notion of uniform speed, which essentially encompasses the idea that distance increases linearly with time. With this uniform speed, Galileo is then able to develop this kind of equality of ratios. In particular, if we have two objects moving with constant speed, then the ratio of their displacements is actually equal to the ratio of their constant velocities multiplied by the ratio of the time in which those displacements occurred. Now, today we would write that as delta x equals v times t with appropriate units. But Galileo instead formed ratios so that he could avoid the subtleties of multiplying numbers that had different units, and that just basically simplified his development to him. Now, we're going to follow Galileo's approach and then develop one of his main ideas that's still used today in elementary kinematics. That being, under uniform acceleration, the displacement is actually proportional to the time squared. And that, of course, being when the object is released from rest. So to begin, we consider Theorem 1, Proposition 1 from Galileo's Discorsi, that being the work he published in 1638. So his theorem reads, the time in which any space is traversed by a body starting from rest and equally accelerated is equal to the time in which that same space would be traversed by the same body moving at a uniform speed whose value is the mean of the highest speed and the speed just before acceleration began. So basically he's saying that if we have an object being uniformly accelerated through time, then the displacement could be equivalently described by the average velocity over that same time interval. And in order to show this, Galileo asked us to draw a few lines representing different quantities. So we let CD denote the displacement over a certain time interval, and then we draw the triangle ABE to represent a couple of different quantities. Specifically, AB will denote the time interval in which CD was displaced, and then from B, we're going to draw the perpendicular to E such that EB represents the largest change in velocity over the time interval AB. Now, because acceleration was uniform, then velocity changes linearly with time. Specifically, EA will in fact actually describe the way the velocity changes with time. Now, we're going to try interpreting this in a with modern intuition just to help us see how Galileo is going to go about this. So suppose that the object began from rest, and then let us further suppose that EB is actually the y-axis and that AB is the x-axis. Then what we have is a velocity versus time graph. And with this, we can then describe the displacement of the object over the time interval AB by understanding the area under the curve. Okay, in other words, the area of this triangle. So, in order to find another object or another motion that traverses the same distance over the same time interval, we then just need to find a different graph that has the same area. And to do this, it seems quite clear that we should draw this rectangle FGAB, namely where F is the midpoint of EB. This is because certainly this portion, FIAB, that area is shared by both the rectangle and the triangle. But moreover, this excess portion, IGA, is equivalent to this deficient area, IFE, so that both the rectangle and the larger triangle have equal areas, and hence the same displacement occurs over the time interval AB. Now, this gives a modern description of how this theorem is true, but in order for Galileo to describe this, he doesn't actually directly apply to the mechanics of area, and instead describes a certain kind of bijection between the instantaneous velocities of the two described objects. So, for example, he begins by saying, let us take the instantaneous velocity here of the uniformly accelerated object and associate it with the proportion of the instantaneous velocity of the uniform velocity object. And then similarly, we associate these instantaneous velocities. But then, after we pass this kind of critical point I, the excess velocity of the uniformly accelerated object will be associated with the previous deficient velocity. And then when we continue this process, it's pretty clear that although the uniformly accelerated object is slower, during this first half and thus doesn't traverse the same amount of distance, then on the latter half, that the fact that it was behind is then made up for with this increasing speed, which is in proportion to the lack of speed earlier, and hence they traveled the same distance. And this concludes Galileo's arguments. With this, we then can go to Theorem 2, Proposition 2, which states that the spaces described by a body falling from rest with a uniformly accelerated motion are to each other as the squares of the time intervals employed in traversing these distances. Basically, he's saying that a body falling from rest under uniform acceleration, then the distance traversed is proportional to the time squared. And again, this is what's used in elementary kinematics today. So to give Galileo's argument, we draw a few lines representing different quantities. Let HI represent distance, AB represent time, and let AC represent uniformly accelerated velocity. Then we then mark off 2 points DE such that AD and AE represent 2 different times, and then we correspondingly mark off OP for instantaneous velocities and LM for distances corresponding to those previous times. After this, Galileo's argument is very rhetorical in nature, so we introduce some symbols in order to better describe the argument here in this presentation. So we let V naught represent the instantaneous velocity OD at time T naught, which is just the line segment AD. And then we let X naught, or HL, represents the distance corresponding to the time T naught. And similarly, we define V, T, and X. Then the claim will have been shown if X divided by X naught is equal to the ratio of T over T naught squared. In order to do this, we begin by noting that due to uniform acceleration from rest, we actually have the velocity being proportional to the time. In other words, we actually get this ratio immediately. Moreover, from Theorem 1, Proposition 1, we can describe the distance traversed on the time interval AD, or the time T naught, by the average velocity, that being V naught over 2. And similarly, we can describe the distance traversed in T by the average velocity V over 2. And thus we get this relation right here. Then dividing out the 2's and then substituting the V over V naught down here, we get the final expression as was desired. But at this point, this gives like Galileo's main theoretical work, or this argument here, which is very useful even in modern elementary kinematics. But if we recall Galileo's timeline, Galileo would often recall observations from his telescope in order to further for example, the Copernican theory of a heliocentric solar system. So here we might ask, well, where is Galileo's evidence that this in fact describes nature? And in fact, if we look at Galileo's scratchwork, we can find such evidence that strongly indirectly supports his theory. So suppose that we have a table that is denoted by this dotted H line, and then above the table we're going to mark off a couple of different distances, 300, 600, 800, and we're going to place an inclined plane on this table such that the height of the inclined plane is those marked off distances. Then we're going to place a ball on each of those inclined planes, let them roll down, and then once the ball hits the table, it's going to gently change its velocity such that it is horizontal to the table, and then it's going to be horizontally ejected. And then we're going to measure the distance, the horizontal distance from impact to the base of the ejection, so the base of the table. Then with this, you're actually able to indirectly show Galileo's theory of kinematics. Now we're going to, in order to actually show how these measurements are useful, we're going to introduce some more notation. Let H denote the height of the inclined plane above the table, so we're just going to fix one inclined plane, and then we're going to let D denote the length of that inclined plane. Okay, then we're going to let T denotes the time it takes for a ball to roll down the inclined plane, V be the speed of that ball at time T, so in other words, the maximum speed of the ball on that inclined plane. And then we're going to let R denote the horizontal fall distance, the distance it traverses horizontally after it is horizontally ejected from the table. From this, we can then actually conclude some proportionalities. So, to begin, we have H is proportional to D. This follows directly because of trigonometry. So if we put an inclined plane on the table, then we're basically forming a right triangle, D being the hypotenuse and H being the opposite leg. And because of this, we then multiply by the appropriate sine of theta, and we immediately see that H is proportional to D. Moreover, D is proportional to T squared because as a ball falls and rolls down, the inclined plane, it's the speed that it gains is proportional. Its motion can be described by uniform acceleration, and hence the distance traversed is actually proportional to the time squared, again because it started from rest. And so we get the first two proportions. For the next proportion, we claim that t is proportional to v, and hence their squares are proportional. And this is because since the ball is undergoing uniform acceleration down the ramp, then because the motion started from rest, the velocity is actually proportional to the time, and hence we get this squared proportionality. And finally, we get this last proportionality where v is proportional to r, and hence their squares are proportional, by a slightly more subtle argument. So this actually introduces Galileo's superposition principle, namely that once the ball is ejected from the horizontal table, so it's ejected horizontally, then we can decompose its instantaneous velocity into a horizontal and a vertical component. And because the only force acting on that ejected ball is the force of gravity, which only acts in the vertical component, then the velocity that's horizontal will actually remain constant and not change. Thus, we actually have horizontal uniform velocity, and since the object will always fall in the same period of time, since, of course, all objects fall in the same period of time, then we actually get this proportionality where r is proportional to v immediately from that. So since we get this last proportionality, we can then conclude that h is proportional r squared. Once we divide with some reference values, we don't have to worry about a proportionality constant, and thus we get thus we can predict the horizontal drop distance by only knowing the height of the inclined plane. And thus, moreover, if we have the height of the table, then in order to compute the drop distance, we have to be taking square roots, and that's what the bottom half of this folio is. It's just Galileo computing square roots. And this actually indirectly, and since Galileo's measurements only had like percent accuracies of like 5%, or percent errors of 5% is what I meant, then Galileo was actually able to strongly support his kinematic theory. Now, we finally conclude this presentation by going over, again, reviewing the main results of Galileo's discourses, which was, of course, the definitive work of Galileo's kinematics. So, to begin, a body will remain moving at a constant velocity unless acted on by another force. This basically gives a precursor to Newton's first law of motion. Moreover, in vacuum with constant acceleration from rest, we have the velocity being proportional to the time. And similarly, for a similar system, we have the distance being proportional to the time squared. Now, what's interesting, of course, as discussed in the last example, a precursor to the principle of superposition of the velocity being decomposed into its horizontal and vertical components was then proposed by Galileo to describe motion. And then finally, we note that the trajectory of a projectile is a parabola, and this basically, it seems reasonable after considering the squared proportionality with time and distance when considering uniform acceleration. And thus, these give the main results of Galileo's discourses, which are still considered relevant today in elementary kinematics. But we do finally remark that Galileo's work did remain incomplete, and this is just because Galileo would always use geometry in order to provide justification, and thus he couldn't glean the algebraic insights that would be necessary for him to better analyze more sophisticated experiments or to further his theoretical analyses. But that being said, Galileo made significant contributions that were considerably more useful than the old Aristotelian philosophies of the past. And thus we give some references, and we thank you for your time.